Chapter 5, the laws of motion. Here we have we have to study the motion of any object, and we take into account the cause of this motion. I mean, we talk about the force F. So the force is the cause of motion. We talk about F in the case of dynamics. Before, in the last videos, we talked about the kinematics. We calculated the position x and y in function of time, the velocity, and the acceleration a. And we used the kinematics equations. Okay, maybe, and we did not talk about the cause of motion F. Sometimes, and by using the kinematics equations, we cannot calculate the acceleration a. It's difficult. Okay, in this case, we need a help. Newton's second law is here just to help us to calculate a by using, for example, F equal ma. From here, we can calculate a, and we come back to the kinematics equations. We can calculate the velocity, the position, the time. So here we have a combination between the dynamics and the kinematics in order to study the motion of any object. First of all, I want to talk about the force in general. The notation, you know, F, okay? It's a vector quantity. F is written in function of the component fx and fy. This F causes any motion and any changement in the velocity. If we have this object at rest, to create a motion, we have to apply F. When you have F, you have a changement in the velocity. I mean, you have A. Because A equal dv over dt. Okay? This is in general. And let's talk now about the Newton's first law. Let's say here, as definition, if the summation of F applied on the object equal to O, I mean F in function of X equal to O, and F in function of Y equal to O, in this case, the velocity V must be constant, okay, which is equal Vx and Vy must be constant. This is a general definition. Let's say here we have a space. In the space, we don't have gravity. So for any object of mass m, we don't have weight because we don't have gravity. In this case, if we push this object at initial time, t initial, we push this object to the right. This object will move with initial velocity vi, okay, at initial time. Because we don't have any external f applied on the object, summation of f applied on the object equal to 0, the object will continue with the same velocity to the infinity. At t equal infinity, the object will have the same velocity vi. Okay, it's constant between the initial and final. And if you have any object here at rest, and the total f applied on the object equal to O, for example, on the table here, in this case, we have mg, and we have the reaction N. In this case, you know that this object is at rest, so the summation of f on the object equal to O. We don't have motion, we don't have acceleration. In this case, the summation of f equal to O, so v must be equal to constant. In our case here, v equal to O, so v equal to O all the time. Okay, remember this definition. When f equal to O, the velocity is equal to constant. Second law, Newton's second law, the summation of f of the force applied on the object equal m times a. Let's say here we have an object on a table. This object has a mass m, so the weight from the center downward we have mg. And we push this object with f1. Here we have f1 and mg. And we have the reaction N like this. Okay. I give a simple example. We have an object in the space, this one, and we apply F on the object. Here we have F1, and we can say, for example, here we have F2. Okay, the total F applied on the object in this case, we have F1 and F2, and the line of motion is in this direction. Here we have the velocity of the object. In this case, V increases. So in this case, A and V have same direction. Okay. Here we have V, So in the same direction, we have the acceleration A. Let's apply the Newton's second law. Here we have the summation of F. We have F1 plus F2 equal MA. Second, we can draw the components of each one. For F1, we have F1x and F1y, and F2 has only x component. Here we have F1y, and here F1x. And you know that the line of motion, the motion must be in the direction of V. And we can say V must be in the direction of the motion. Okay? Okay. We can write now F1 equals to F1x plus F1y. F2 has only F2x. We don't have F2y equal M. Here we have AX and AY. Okay, in this case, as you see, A has only X component. We don't have a Y component, so we can cancel AY. We can write this equation in function of I and J. In this case, I in this direction, in the line of motion, and J like this. F1x is in the positive I direction. We write F1x as absolute value in the positive direction. F1y is in the positive F1y in the positive J. F2x in the positive direction F2x equal MAX in the positive direction, we can say AXI. We don't have J. We have 0 J. To solve this one, we have to take the I here, and I here together, and for G component also here we can take the G component. In the case of Newton's second law, the general equation F equal ma. Okay, you know that F in Newton, m in kilogram, and a in meter per second square. F can be written in function of the components. We have Fx plus Fy equal m, and Ax is equal to Ax plus Ay. We have a lot of application with Newton's second law. We can talk about this later, but in general, when you write F equal ma, you must have summation of x equal max, and the summation of fy equal to may. And if you have z components, you can say summation of z equal maz. In general, in our study, we study only 2 dimensions. Okay. This is about the second Newton's law. Let's talk about the third Newton's law. This law, in general, we have to study the action and the reaction. For each action, you must have a reaction. The action creates reaction. We can give a simple example. Let's say here we have a table with an object on this table. This object has a mass m, so we must have the weight mg. Here we have mg created on the object and directed downward. This one is mg. This mg is the action of the object on the table. This action will create a reaction from the table on the object. It must be applied from the table on the object in this direction. So here is n. Here we can say as magnitude, the action equal the reaction. Okay? But as direction, mg is opposite to n. You can get this result by applying Newton's second law. Because in this case, we don't have motion. So the acceleration equal to 0, and you know that F equal ma equal to O. Okay? In this case, we have n and mg. So n plus mg equal to O. So n equal minus mg. So the action is opposite to the reaction. Okay, as a vector quantity. But as magnitude, you have to say n magnitude equal mg magnitude. I think it's all about the Newton's second law. Let's tell you just about when the object is at equilibrium. Okay. Here in the case, if we have a particle in equilibrium, it means the object is at rest. Okay. It's at rest, so the summation of f equal to 0, and the x component of f equal to O and y components of f equal to O. Now I am talking in the case of the linear motion. Later, we have to talk about the rotational motion. We have to add another parameter later. Remember that if I give you a simple object in equilibrium, in this case, you have to write the summation of f equal to O, fx equal to O, fy equal to O. any object in equilibrium, the summation of F equal to O. Thank you.